There you go. All right, welcome everybody. This is Joe Armstrong, and you're on the Power Systems Virtual User Group webinar for November. I don't really have any announcements today, so we're going to kind of jump right into it. Today we have Earl Jew talking to us about the numbers associated with mpstat, vmstat, and iostat. And if you don't, if you look at these and you look at the numbers and you haven't ever looked at them before, they can be pretty confusing. Now, if you've been studying this stuff for years and years, I'm sure you're pretty comfortable with looking at it, at least what they are on your systems, and that's great. But if you're not, I think Earl has some great stuff to share with us. Now, I don't think there's any real rules to this stuff. This is what Earl has noticed over the years of his experience that he's going to share. And if you listened to Earl before, you know he can get pretty deep. So try and hang on. There's a lot of numbers in some of these slides, and this is what, I think of it as in the Matrix, that guy that looks at the screen, with all the numbers rolling down and he could see things, where the rest of us just saw numbers scrolling down. Well, that's Earl. He looks at these screens. He's the Matrix guy, and he sees things in them, and that's what he's going to share with us today. So a little bit, and I didn't even look up Earl's bio here, so just what I know of him. A little bit, Earl's with lab services. He's been a long time at IBM. He's been doing performance stuff forever since I've known him for many years, and he has a really unique way of talking about performance tuning on Power Systems with AIX, and it all has to do with looking at these numbers and understanding what they mean and what they're telling us about your systems. So with that, Earl, I'm really glad that you could join us today, especially on the short notice. Thank you so much, and I'll turn it over to you.
Okay, good morning, everybody. Thank you for this opportunity. I written something here that stands alone without me. What I mean is you don't need my voice to benefit from following this particular presentation. It should be, I'd like to think of it as an enduring reference that will be usable long after IBM does what IBM will do to me. Okay, so trying to get this thing to advance. There we go. The numbers of AIX. All of us are always monitoring, but these numbers are otherwise nonsensical without guidance. If you don't know what the numbers mean and what's high or low, okay, you're monitoring and they're paying you to monitor. But the point of monitoring, of course, is to make decisions. The point of monitoring, of course, is to decide whether you need to give it any attention. Wow.
Yeah, what's with little music in the background all of a sudden?
It's not here at this Phoenix site.
All right. Well, you keep going off. It keeps happening. I'll have to try and figure something out. Everybody should be muted.
Okay. This is 15 years of me doing this kind of work, more than 700 customers, mostly provided free for the joy, and I get lots of practice doing this. This is why I keep inviting everybody to let me help with understanding their workloads, maybe tuning them. Just have a look, because it gives me practice too. There are no references for this kind of content anywhere. No red book, no nothing. It's just me and this. And I don't always understand why what I'm about to show you works, but after practicing for so many customers, it does work. It's just that it eventually starts to talk to me. So that's what the word conjecture that works means. I don't always know why it works, but it does. It's kind of like acupuncture research. This is Gilligan's Island, the theme, but it's mixed in with others. What to know? I'm going to give you an introduction to the commands that we're going to look at. This is Marianne, and vmstat IWWT1 is what I hope all of you would begin to use and collect maybe into a text file, because this to me is far more indicative. And what's great about it is every second you get a new line popping up across the bottom, and the history of previous seconds is scrolling up the screen while this is running. Okay? Instead of using your iPhone to video record Topaz, Edmond, or something, so you have a history of past seconds, this here gives you the past seconds as it pops up the screen, so you can notice dynamic changes. It's a great advantage. And of course, I advocate monitoring at 1 second because AIX won't give me stats any faster than 1 second. This is the real-time root of where these rules of expectation begins and ends. We're going to go through every one of these columns left to right, and you begin to see that the picture that you see in just digit count alone is useful. Okay? So we're going to learn about monitoring. Marianne's shared processor LPAR 9 entitlement 12 virtuals SMT4 almost 200 gig on an S824. Now, I identified the server of each of these characters in Gilligan's Island and Game of Thrones and wherever else, because we always need to tune according to what the architecture, technology, and configuration is. That we always need to know that you can't tune a big LPAR Power 9 the same you tune a small LPAR Power 5. Okay, so always need to acknowledge the hardware. Here's Marianne's mpstat. This is vmstat. And mpstat, this is 1 second of data, right here. 1 second of data for all 48 logicals, while up here, every line is the summary of the entire server. Every one of these seconds on vmstat is a summary of the entire server. Well, being that it's the summary of the entire server, the bigger our servers get, the more one line of stats are averaging and adding a much bigger workload, a much broader concurrent multi-part workload, which is where this mpstat gives us the details of. So as our systems get bigger, we need to delve deeper into the detail of the meaning of these numbers. That is what I was saying. 1 second of vmstat above explodes to all the lines of detail in mpstat below. So there's a whole lot more we can see with mpstat. And of course, the all lines of mpstat with rounding error and of course misalignment of time do map to the 1 second line on the top there with vmstat. So know that these numbers do map to one another, but they're never exact because alignment of time. mpstat-A, power 8, this is Marianne, and -A is everything. -A is all, right? That's Kenworth. That's power 9. That's SMT8. And the one thing you see that is really different with power 9 is this column, %NSP. Notice %NSP is the average clock cycle of all SRADs over the last second. This clock cycle here, 140, is the average clock cycle of all SRADs over a second. What I need to tell you is on Power 9 are, I guess, overclock speed or faster speed or workload optimized frequency. It can change its clock cycle every 4 milliseconds on every SRAD. It's amazingly fast. So between this second and the second down here, the clock cycle went from 140 down 137. If you've been watching Power 8, the clock cycle is rarely, if ever, over 105 for overclock mode. And on Marianne, the column is not there at all. Oops, on Marianne, the column is not there at all. So we have a new dimension of workload optimized frequency for Power 9, which changes a lot of things for us. Here's Marianne on iostat. I always call this iostat dirt, but that's really a capital D, lowercase l, cap R, cap T. This is a 60-second interval, 10 intervals. Okay, we're going to go through these stats and how to see it. We're going to Ginger. It's different LPAR. 32 dedicated cores. Terabyte of RAM on a E870. Ginger's got a late and lucky workload, meaning it's a late piece of software that uses shared memory and exploits multiple threads in a process. 18 memory pools. So this gives you a base, and we're going to go through each of these columns And these numbers, once we return to the slide way below, should take on entirely different meaning when you now have formulas for understanding what's high or low. There are our concurrent composition of different threads, right? Classic run queue, B, P, W. But what we're running here in this run queue are threads of the executing process. KTHRR is the run queue of running plus runnable threads. And better state this again and again, this number under the R column only has meaning, especially at 1 second, only has meaning if you know this number here, the LCPU count. That the run queue value only has meaning if you have this number up here. Otherwise, if you don't know what's 128 logical CPUs, the meaning here is lost. But what are the running plus runnable threads TIDs executing on the run queue? You see something's running there, wouldn't it be good to know what they're executing? Well, let's show you how to do that. This slide is worthy of a poster printout. Well, that's just me. Here are the various syntax of commands that I use, and we'll go through them. We're going through this one right now. This one will be addressed at another webinar in 2019, okay? And we're going to go through how to see it. We're going to focus in on this question: what's the LCPUs, logical CPUs, executing on the run queue? Well, we're going to focus on right there, intensity. Intensity uses this syntax. Intensity regards individual processes and their density of on-CPU threads within a second, which is what I was telling you KTHRR is showing us. What's executing in the last second? There it is. PS-EF, we all know that command. Pipe sort-NK4 presents us with this. Now, of course, there are many more processes above, all the way up to the heading line, but this here is the bottom of the slide, and we're going to zero in on the C value. The C value is the total count of CPU time in clock ticks. Clock ticks. The definition of clock ticks is synonymous with decrementer interrupts, and the standard decrement interrupt is 10 milliseconds, which maps to our understanding of Power VM's interval. Clock ticks, though, can be variable in length. The clock tick can be mere nanoseconds for very fast, or it could go out to 100 milliseconds if there's no workload. So the clock tick is a variable amount of CPU time. Non-zero values in this column, which is the fourth column, which is what NK4 does, the non-zero value defines the intensity of running processes. That means down here, this DB2C process on the bottom had 285 clock ticks in the last second. That means a heck of a lot of threads ran on CPU in the last second. Every time you execute this command, the numbers are completely new again. It only gives us the last second. That means the C value here is not cumulative between seconds. This defines the real-time workload and the intensity of the workload. See this C equals 0? That means the process didn't run in the last second. Single digits, it ran lightly and or incidentally in a second. And here, these 3 digits, that's really cooking. S time. S time is the start time of the process, if less than a day old, or a calendar date of the process of greater than a day. So calendar dates means they're long life persistent processes. If it's a clock time, it's a more recent process that just got started. So these processes down here just got started rather recently. While, of course, these bash shells got started days ago. Persistent. Persistent is my word for a process that exists whether it's running or not. Big difference from my much younger days. Today we have processes that exist but maybe never run. Processes sit there, take up memory, and never run. Why do we do that? In our 64-bit architectures, many of our processes exist and never run because we recognize that the overhead of creating a process is a workload, and it takes time to create a process. As we advance through later and later software on larger and larger scale systems, I believe our applications will begin to make a lot of processes in the beginning and leave them in memory so that when they need to execute, they immediately execute without having to create the process. So we will see a larger share of persistent processes with calendar days that may hardly ever run, but when they do run, they run immediately. No longer is it the small memory assumption that, hey, let's create a process, let's run a process, let's kill that process to save memory. Hey, we need to run that process again. Let's go and create the process, run the process, and then kill the process to save memory. It's a big deal. Growing into the architecture. C and S time help to distinguish processes that are intense burst OLTP. We have to tune differently for OLTP, or long duration batch, or if the C value is single digits, I call that lightly and incidentally executing. Yes, they're my arbitrary definitions, but that's what I'm here to do, is to tell you how I do things. And of course, persistent and not running, which is most of our process, C equals 0. Again, every time you re-execute this syntax, all this is renewed for the most recent second. This, to me, is the ideal way to understand the real-time workload. Time. Time accounts for the minutes and seconds. There are no hours in this number. It's minutes and seconds of on-CPU time since the process was created. Well, if we know when the process was created, S time, and we know how much on-CPU time it has accumulated, I have invented the word cumulative intensity. That means the on-CPU time in seconds divided by the seconds since the process was started gives us the ratio of cumulative intensity. Okay? So processes could be created just mere minutes ago and maybe accumulate a lot of on-CPU time. That is massive cumulative intensity. Or a process could be created days ago and have no on-CPU time, not even 1 second, which would be, of course, a very extremely nil cumulative intensity. Another concept for us to play with. All three of these columns gives us a real-time snapshot of the user workload. If you want to see the kernel workload too, you change that E to the letter K, and now you see what the kernel workload does. Very uninteresting. What are you going to do? Remove the kernel? When any process is terminated, this process data is also lost. That means if a process is no longer persistent after termination, which is not, of course, this data is gone. So if you want to record the real-time data of processes coming and going, all you can do is record it, execute it often, and record the snapshots often. Okay? Because the processes are coming and going. Once they're terminated, this data is not there any longer. You guys are accustomed to that. Most of us are using those other tools, and the data is gone once it's off the screen. Hey, this is what I use to tell what is running and the intensity of what is running. When this C value is over, is 2 digits or more, I call that the real workload that's running. The Powerverse uses other tools offering fewer details when searching for the same. I think this is easier.
What are the last two digits in that column next to the 60, 13, 5, 11, 4? What are those numbers?
This is a DPF environment. It's a multi-partition. So that's
Okay, so we're going to want to see what threads are, threads TIDs, because that's what I told you. We're going to figure out what are threads. We're going to go do a PSMO thread-P on the PID down here that is the most active. Let's take a look at what threads look like, right? Because this is just processes listed here. Coming back, I want to explain that this shows us the fundamental structure of process threads, and that's what that PID looks like. Now, let's go through what this PSMO thread-P PID shows us. This, of course, is breaking down. First line of PSMO thread is about the process. This is the process here. It shows the CP priority and suspend count. The process has used 440 clock ticks over the last second. CP equals 440 of all threads. That process ran that many clock ticks, priority, and the thread count. Suspend count is the count of threads that comprises the process. This DB2 process is made of 198 threads, running at priority 40 for the process. But now we go to threads. Not all threads run at the priority process priority. Threads have their own independent priority, which you see here is a higher number, lower priority, than the process itself. That is that the threads can selectively run on assigned priority. Though authorized to 41, it could run at a lower priority. Okay? So the TIDs, the thread IDs, they're unique and odd numbered. The TIDs are what we're running on the run queue. We execute threads on logical CPUs and not the classical executing processes on CPUs. Okay? So the run queue is actually comprised of TID threads. The state, ST, is running or sleeping, and that means down here, this thread ran 25 times in the last second and is sleeping at the moment of execution of this command. This thread ran 15 times in the last second and it was still running during the execution of this command. So sleeping and running. You can have something that ran but doesn't run anymore, or you can have something running 22 and still running. And these thread counts, I said thread count, not process count. Thread counts stop counting at 120. That means you'll never see a thread counting higher than 120, but you could just assume that if it hit 120, it probably runs a whole lot more than 120. We just stop counting at 120. What's this noise? The thread priority and suspend count. Suspend count equals 0, it's sleeping. Suspend count equals 0 here, it's running. Anyways, that's what that is. These TIDs with CP greater than or equal to 10, those threads are the long-running TIDs of the user workload. First premise. The user workload is a long-running workload. Well, the meaning of long-running, to me, is 10 clock ticks in a second. Now, of course, long-running batch jobs, they may run for days. But long-running in this world of power, to me, I'm going to draw the line at 10 clock ticks in a second. So let's call that a long-running workload. Why? The kernel workload is extremely short duration execution of threads. And compared to what I call long running is very long compared to extreme short duration of kernel thread execution. Okay? So these are long running TIDs of the user workload. Joe, am I going too fast again?
I don't think so.
And the user workload that we care to tune is mostly comprised of these long-running TIDs. What I'm showing you here is how to identify the workload that is running. Because until we can identify the workload that's running and the intensity, density of thread execution, until we can identify that definitively, we don't know what to tune. If you can't see what's running and how hard it's running, you don't know what to tune. I mean, in the old days, I would just type PS and the processes just show up. That's what I'm going to tune. Today, you can't assume that. Just because a process exists, if it isn't executing, why bother trying to tune it? This is how I tell. This series illustrates how CP greater than 0 for TIDs, threads, same thing, comprise the run queue. So I'm making a mapping of PS command output to that KTHRR run queue. The run queue is comprised of running and runnable threads, and the TIDs, or threads, whichever one you use, are executed by these logical CPUs. Cool. Using this syntax here, I'm stating and drawing a line arbitrarily in the sand that if CP is greater than or equal to 10, we can now see what are the long-running threads of the user workload. Key concept in this tuning tactic. Understand what I mean by long-running threads of the user workload. More later. So, first slide. This is Power 8 only. When I say for AIX Power 8, it means don't use this for AIX Power 9. And when I say for AIX Power 9, it's only for Power 9. And in some slides we'll say, hey, this is cool for Power 8 and for Power 9. So looking at the run queue and mapping it to the LCPU count, this LCPU count will be different on your LPAR. That's why it looks like your LCPU count. Here on this LPAR is 128. You have a formula for mapping the value of the run queue to the SMT mode. If the R value is 25% of LCPU, it means your SMT1 with one thread per virtual. It's a direct mapping that you can see. If the run queue is greater than 128, you're doing critical overthreading on Power 8. If the run queue is higher than LCPU count on Power 9, that's normal because that's Power 9 technology. We need to note that we tune and monitor according to the technology. And Power 9 is markedly different from Power 8. Yeah, all of it looks like AIX because it is AIX. But we need to know how they're different. This here talks about SMT4 and SMT2 on Power 8. Those of you who know me, I always scream at you, thou shalt not implement SMT8 on Power 8. But if you're on Power 9, you had better be on SMT8. So let's look about how to tune KTHRR. The rules of expectation for understanding the R value, to me, my new methods are refining it in 2 steps. These are the 2 steps. We first monitor user plus system time for vmstat, and then we monitor the CS-ICS ratio of mpstat for understanding what's going on the run queue and tuning accordingly. We're going to talk about these 2 rules of expectation further below. Remember, this methodology is Power 8 only. This is Kenworth. Kenworth is Power 9, S922. For Power 9, we monitor from the other end. On Power 9, if your idle plus wait is 0, and it's, I call it critical overthreading, if you have 2 columns of zeros, meaning it's sustained. If you have 2 sustained columns of zeros, you are in critical overthreading for Power 9. If you have one interval of 0 and 0, and it's not sustained, then you're otherwise, I call it momentary exhaustion over the interval of 1 second. Idle plus weight. If it's 2, it's a bare minimum of logical CPUs. 5 are proper minimum. And the ideal range should be 6 to 28. That's the sum of idle plus weight. Why? Because at idle plus weight equals 28, we have SMT2 equivalent expectations. That means that what we use for SMT2 on power 8 would be equal to 28 on power 9. And if you're sustained at greater than 40 or equal to 40 on idle plus weight, you just have too much CPU that you're not using when sustained, right? Now, the whole point of that is this. We ignore the R column and focus on idle plus weight. That screaming there, say what, means, why am I teaching to ignore the run queue? It's because of the technology. Power 9 technology is different. On Power 9, we cannot tune by the run queue, and I'll prove it. Here is ARIA. ARIA is a different workload on Power 9, S922 at SMT8. In green, I ask you, do you see it too? Well, we'll take a pause here. You look at all those numbers, and do you see something different about this LPAR? From what I've taught you, do you see, I'm trying to get my icon, do you see that the run queue here is a little bit higher than 64? This is my first exposure to Power 9. I was on customer site, and I started having an allergic reaction when I saw the real-time workload Power 9 for the first time. And he said, what you freaking about? It's running fast. You see, these numbers would be a crit sit Power 7, Sev 2 on Power 8. But there's more than that. Right? I mean, there's much more to what we're seeing in these numbers. I'm going to show you what they are. So, the run queue is erratically high for 64 logicals, but yet watch. The EC value is going above entitlement, below entitlement, it's going up and down, and that run queue kind of goes from very high down to a single digit. This is wild. Next, P and W columns. You guys are not accustomed to the P and W column. The P column is the number of raw I/O requests, Oracle ASM or raw, I/O requests on the run queue. That's the average count of I/Os they're spinning in 1 second. The W column is the count of JFS2 block I/Os on the run queue, whether it's CIO or direct. So these run queue values are so high, they're abusing the SAN. As a matter of fact, this workload would run a lot faster, but the SAN is completely being abused here. It didn't care in these 3 values here, interrupts, system calls, context switches. This profile of digit count is an enterprise class workload still running. And it's imbalanced by the ratios, which we'll identify. And yet the B column here is always 0, meaning there are no threads blocked. It's just cooking along. Yet, throughout all these many seconds, the idle plus wait, except for this one interval of momentary exhaustion, is higher than 6. I mean, I said 2 is the minimum, 5 is the proper, 6 to 28. This means there is still headroom. Despite this high run queue, there is still headroom to run more threads in the 1 second interval. This is our new reality of AIX on Power 9. I announce it now. We have to learn to monitor Power 9 differently because the technology of the core is totally redone. So, ARIA, it demonstrates why we can't tune by the run queue anymore on Power 9. If we can't tune by the run queue, I introduce tuning from the other end. That is of ensuring there's enough idle plus wait to note exhaustion or underutilization or what have you. Okay, so idle plus wait together. This is for both Power 8 and 9. This talks about BPW, just like I talked about, the run queue of block threads, raw I/O, JFS2, and what are high and low values. Well, here, this is high 2 digits and 3 digits, and what do I say? I say 3 digits, critical focus on the rules of expectation for iostat. A warning, these 2 column values here are telling me you got a problem with I/O. Now, just because these are running 2 threads doesn't mean that adding CPU will make those things count go down. No, it deals with the SAN I/O, okay? So I'm giving you a sense of, hey, single digits, cool. Heating up, warning, critical. This here, it's got a problem with SAN. Now, what that problem is, that's the next level analysis. Memory, AVM. Computational memory is AVM. Do not think AVM is average memory. AVM is active virtual memory, which means it's computational memory. Definition of computational memory is all of AIX and its memory buffers and all of the executing workload is active virtual memory, is computational memory, is working memory. It is the memory of your executing workload plus data that's internal to your application. Your memory pools of DB2 and Oracle. Data is in computational memory. Free memory. By the way, AVM and free memory are in 4K mem pages, so there are counts of it, right? Ginger has 18 memory pools. What's the amount of free memory that you need? How much do you need to maintain? Well, let's talk about it. Here, I talk about active virtual memory and how to calculate what is the proper amount of computational memory. So you calculate out AVM in bytes. AVM in bytes, that means you take this number and multiply it by 4096, that's AVM bytes. You look at your megabytes, multiply out by megabytes, and you get memory in bytes. And now I say computational memory less than 60%. You got to grow your shared memory segments to hold more data. You got to use the memory you got. 60 to 80, perfect. 81 and 90, risky and running slower. Now, why, when computational memory at beyond 81% is risky and slower? Well, when computational memory grows, your file cache shrinks. And when your file cache shrinks, the content that remains in file cache is more recently used. That means the old stuff is already flushed. The reason why it's risky and slower is free memory comes from your file cache. If your file cache is too small with new content, LRUD cannot free that memory quickly enough or as quick as usual, and you often need free memory to create processes. Often, don't know how often. Everyone, if you don't have free memory to create a process, how fast can you execute that process that doesn't have enough free memory to be created? That's why it's risky and running slower. The new concept is how quickly and conveniently is free memory made available. Enough said. When computational memory goes beyond 91%, you're liable for paging space, page out performance issues, which are not IBM support problems. It's a performance issue. Paging space, page outs are normal. Just not cool for performance, which is why we want to ensure you have enough memory. Okay? All right. Next, this here is going to take some study. I'm not going to go through in detail here, but if you study enough, you understand how to set the minimum amount of free memory. For small LPARs on Power AIX, you get about 4 digits of maybe 5 digits of free memory by default. This gives a formula where the more LPAR memory you have, I say you need to maintain a higher amount of free memory. Here shows an overly generous 8 digits of free memory. I don't care if you're a 16 terabyte memory LPAR, no one ever needs and can use 8 digits of free memory. It's too much. High 7 digits at a terabyte is the most you ever need. Never a need for 8 digits, okay? So I'm trying to add some sense that the larger is the memory of the LPAR, the more free memory you need, because usually you have more CPU and you can absorb and use free memory, greater intensities in a spot of time. Anyways, study this, and it's right. Next columns. These are pages. And I'm talking about FIFO. FI is the count of your default and RBR reads. No raw, no CIO, no MMFS. That's GPFS spectrum scale technology, and no NFS. So the FI is reads, normal and RBR, and FO is default writes, default and a release behind write. Well, how do you know if these numbers are high or low? Well, I'm going to tell you. If FI plus FO is 0 to 2 digits, you're just at home watching a DVR. So on and so forth, by the digit count of FI plus FO. Like, if FI plus FO is 5 digits, which it is right here, you're racing in a marathon. If you're ever 6 digits like you are here, you're Olympic sprinting. It's really cranking. No matter how long I've tried to look, even on the largest LPARs with 2 flash systems on it, I've never seen FI plus FO at 7 digits. If you see FI plus FO at 7 digits, you did the column total of the wrong columns, because it is not possible yet. Point of this here is, it is cool to have more free memory than the maximum of FI plus FO. Yes, this is too much free memory for FI plus FO here. That's why I say 7 digits is probably the most you'll ever need. Because these FIFO IOs go through free memory. Isn't it cool to have enough free memory to receive and stage your reads and writes? If you're doing FIFO higher than the amount of free memory, you're going to lock up on LRUD. Okay? PIPO, paging space pageouts. Well, paging space page-ins, PI, is no concern at any value because it's not considered, it's just like data I/O. I don't even monitor PI because, you know, you can't have any paging space page-ins if you have no paging space page-outs. Well, it's pretty simple. It's almost always 0 these days, 2 columns of zeros. But if you have a non-zero 1 second, you should be freaking and trying to figure that one out. If you see non-zero sustained PO, you got some real issues today. You've got to recognize that today is different from yesteryear or yesterdecade. Anyways, column 0 and 0 is perfect, and most of you should be maintaining that. Here is FR, SR, the free rate of LRUD adding to the free memory column. That means this FR free rate is adding its memory to free memory. The scan rate of LRUD is SR. And there are 2 versions of this. There's a traditional version of this, rules of expectation, and scaled. Let's go traditional. Valid for power 8-9. If you're 0-0, like you see here, you're late and lucky. You don't use LRUD. You're not using much free memory, if ever. And if you're 0-0, the 1 to 4 bursting up and down, that's normal. That means this ratio, 1 to 4, bursting up and down, that's normal. Where it gets bad is if you're sustained 1 to 5 and higher, sustained, that means it doesn't vary a whole lot. You got some real problems. You're heavy use of free memory, and you need to restructure your data I/O. You have overwhelming LRUD activity, not good. Real bad is if you're saying it greater than 1 to 10. Now LRUD is rocking like mad, trying to make free memory from a file cache that is full of really recent stuff. That's when free memory comes too slow and hangs up everything. That's traditional. Going to scaled. Scaled versions for your very large LPARs, and we don't even look at the FR value. We only look at the digit count of SR Beyond a certain size LPAR, you must go scaled. And basically the same rules. 0, 0, nothing, 3, 4, 5, bursting, that's normal. If you're sustained at 5, it's hurting. And if you're sustained at 5 or 6 digits of the SR value, you got a real blithering problem. The next slide is our favorite old man. This is Mr. Howell. Mr. Howell is a very big LPAR at 8 terabytes of RAM. This has got, I think it's got 2 flash systems on it. And you can see its SR value is 5 digits, 6 digits, and 7 digits. This illustrates amazingly overwhelming LRUD through the file cache, and something is fundamentally wrong denotes that, hey, look at all the free memory I'm making and I'm scanning so hard for. Wait a second. Why am I making free memory if I've got 9 digits of free memory? Why do I need free memory at all when I've got 9 digits free? This is an example of what I mean. Something is fundamentally wrong. It's not a support issue. It's doing just as it was designed. But let's put a little sanity in what's going on. This is why I came up with the rule. Back to Ginger. We're going to look at these 3 purple columns. Summarize it again. The threads on the run queue are running with the IOs on PNW in the computational memory, AVM memory, active virtual memory, and it has this available free memory here to move these IOs, and these threads are invoking this many IN device interrupts for this many context switches, which execute this many system calls. Let's put our mind to what I'm going to tell you. 72 threads were chopped up into 486,000 context switches in 1 second. Guys, you got 72 long-running threads and you chop it up almost 500,000 times in 1 second to run across 128 logical CPU. Can you understand the granularity of execution and management? Now again, to me it's wild. Taking 72 long-running threads and chopping it up 500,000 times. Just the atomicity, granularity of the execution today. And these context switches coming on and off logical CPUs in a second executed these system calls. I'll tell you bluntly now. Only the user workload executes system calls. These 3 columns is the genuine execution of your workload. Device interrupts, bringing data in, taking data out, to threads that are being chopped up for short-term execution, cranking out these system calls. These 3 columns should be key to our monitoring of productivity. A loose ratio, very loose, of interrupts, system calls, context switches, apparently confirms sufficient CPU capacity. I'm saying that this should be a digit count ratio that you see kind of loose here. Oh, this is digit count. This is value. All right. Now, the caveat here is, one time only in all my years, I found a workload that didn't have any system calls. I don't know. I don't know how that happened, but one time I found it, I got to call the exception. Use this as to confirm, not to decide, and there is sufficient capacity. What I mean is the lowest count of virtual CPUs to attend these rules of expectation ratios. What's my concern here? My concern is this. Why am I concerned with these ratios? My fear is you have more context switches than system calls. The user workload executes system calls. If the duration of chopping up your long-running threads is so short per context switch, it will not be able to grind out system calls. What I'm saying is the CS-ICS ratio, when you have the CS-ICS ratio dropping below 3 to 1, your short-running threads begin to preempt your long-running threads. And your long-running threads, it's what's cranking out system calls. If your short-running threads are preempting your long-running threads can't run long enough to produce system calls. That's why this ratio is key to understanding. Oh, exception. Your VIOS doesn't do system calls. It does a whole lot of device interrupts and hardly any system calls or context switches. So VIOS is lopsided. Don't even freak over that, right? Anyways, there's a cut short effect when your short-running threads early preempt your long-running threads. It's less pronounced on Power 9 versus Power 8, but stay wary. That's why these 3 columns are important. The next 4 columns. Well, this is a dedicated CPU part. Ginger doesn't offer PC and EC because it's a dedicated CPU part. But we're going to go through those 4 percentage values, user system idle wait. On a dedicated CPU LPAR, these are percentages. User system idle wait are percentages. And in a dedicated CPR, they are percentages of all cores on a dedicated CPU LPAR. Coolest thing to note, all 4 of these numbers, when you add them together, is always 99 or 100. 99 for rounding error, right? I have never seen it at 101, but I still put plus or minus. Okay? So you can always count on all 4 of these numbers adding up to 99 or 100 because they're percentages of all cores on a dedicated CPU LPAR. Cool. Power 8. My toughest job is convincing the Powerverse. I'll let you guys guess who the Powerverse is, okay? My toughest job is convincing the Powerverse to adjust the virtual CPUs to run in the groove. If you're Power 8 SMT4, the groove is 60% or greater of user plus system percentage with idle plus wait at greater than 2. That's the groove. That means you control the count of virtual CPUs to run in the groove. Okay, now you might be thinking, why is the groove set at greater than or equal to 60? Of course you are all asking that. The reason why is 60% is the beginning of saturated SMT1. I'll explain saturated SMT1. Saturated SMT1 means all virtual CPUs are folded up and executing in SMT1 mode. Okay, so at 60%, you know that all your virtuals are up in SMT1 mode. And greater than 2% means, on Power 8, greater than 2% idle wait means you're not overthreading. See, 2% idle plus wait is equal to SMT4, 3 threads running, 1 wait process. We'll get to that. We'll show you later. Okay? Now, if your user and system is less than 60%, you have unexploited CPU and virtual CPUs, and not using the CPUs got is an efficiency concern, not a performance problem. What I'm trying to show you is don't have an LPAR that is too wastefully too big. That's a bigger issue today than not having enough CPU. This is a shared processor LPAR, Power 9. The same percentages mean the same thing here on Power 9. My toughest job is trying to get you guys to run Power 9 in the groove. The groove is 72% with idle plus wait greater than 2. Shared processor LPAR is shown here on Kenworth. Hey, I need to back up here. Look at this. User percent of ENT. You see, this user percent 74% is 74% of ENT when EC is less than 100. This is not 74% of the PC value. This is 74% of ENT when EC is below 100. And these are user percent 74%. Well, there's nothing over 100% here. But the point is these percentages are of the ENT, of the entitlement when EC is below 100. This is a new finding and a surprising finding for me. I've been teaching you for years that these are percentages of ever and always the PC column, and I got corrected. It was shocking. Sorry, I am wrong sometimes. Why? The documentation doesn't show us this, so I'm sorry. These are percentages of ENT until EC goes over 100, and then they become percentages of the PC value when EC is over 100, and that's real, and that's been proven by many who have been shouting at me, okay? Hey, why is Power 9 SMT8 groove at 72%? It's because 72% on Power 9 SMT8 is the beginning of SMT2 equivalent expectations. You're not actually in SMT2, but you're running at that level of SMT2. And if you're less than 72% user weight, you've got unexploited capacity. Again, a limitation on how not to have too much that does nothing. Efficiency concerns. Here's Marianne. Hey, Marianne is running over 100% EC, which means the user percent is 91% of the PC value because EC is over 100. It is not 91% of entitlement. It is 91% of the PC value when it's over 100. We got it. We got it. Okay. So mostly this is running in the groove, except that we do have some intervals of idle and wait that are less than 2. Right? There's 1, 2, 1, 2, 1, 2. So it is really at the edge of capacity. Also, Marianne is running over entitlement. That means, you know, over 100% here. This should be a decision based on your workload's performance priority. Like this might be a non-prod LPAR, let it run over entitlement. It should not be an accidental oversight that you're running over entitlement and then you start saying, hey, how come I'm not running fast enough, right? Mrs. Howell. Mrs. Howell, as you see here, is violating the rule of my power verse. It says user plus system greater than or equal to 60. Well, it's not. It's far below 60. And look at the idle is very high. Okay? So this is too much LPAR for too little workload, and I get mad at you guys. There are a lot of LPARs like Mrs. Howell in the power verse. If you continue building wasteful CPU LPARs, don't blame IBM if your server productivity is not cranking. You built it wastefully, and we've been telling you for years since Power 5, don't configure too many virtual CPUs you can't use. It adds to the power hypervisor overhead. All right, enough yelling at you guys. Going back to something new, which I can't blame you for not knowing. Refining how to tune for KTHRR by vmstat user plus system, which is the groove that I was telling you about, and then the CS-ICS ratio, where I was telling you where if the ratio is too low, your short-running threads begin the early preemption of your long-running threads. These are 2 rules, and mind you, these 2 rules influence R, but we're not tuning by R. I think this one's a big one. If you're running SMT4 OLTP workloads, you should maintain user and system between 60 and 74. Yeah, I know you should be, I told you between 60 and 98, which it is, but now I'm refining it. Tune the counter virtual CPUs for SMT4 OLTP so you run at 60 to 74%. For batch, you can go at a higher percentage. Why? Well, batch, you care about throughput efficiency. OLTP, you care about thread responsiveness and performance. What am I saying? There. I said it. Right there. If you're OLTP, you want to be running at 60 to 74 because you're going to be only using SMT1, SMT2 modes for OLTP performance. That means a short life, long-running thread will run on more of a core if you're SMT1, SMT4. If you're running batch, you don't care about thread responsiveness, or you don't have a batch workload, okay? I mean, it's about throughput efficiency when it comes to batch. You don't need to keep CPU available for thread responsive in batch, so you run at a higher utilization, 70, 98%, so you only use SMT2, SMT4 modes, and efficiency is real good. Gilligan, SMT2. How do you know it's SMT2? There are no SMT4 LPARs with 26 logical CPUs. Yeah, I guess this could be SMT1 with 26 virtual CPUs, but no, it's SMT2. SMT2 is very undersung in Power 8. SMT2, for OLTP or batch, you have to run at 64 to 94%, whether it's batch or OLTP. And I tell you now, should have told you years ago, SMT2 LPARs are exceptional for mission-critical service. They absorb anything you can throw at it, and it reduces waste. There's not a whole lot of SMT4 waste in idle CPU, because there is no SMT4. Trouble is with SMT2 is you need more virtual CPUs to be configured on more cores versus an SMT4 LPAR attending the same run queue. Right? You need more CPUs. Say it again. SMT4 on Power 8 is very much undersung for the need of mission-critical, highly resilient service. So there's my summary slide. This is how to run in the groove per the character of your workload. Rules of expectation, user plus system, are further refined by this CSI-CS ratio. We're going to talk about this CSI-CS ratio now. Oops, not quite yet. I got to talk about idle plus wait. Idle plus wait reports the capacity to run more threads with an SMT2 mode upshift. It's idle CPU capacity. If you do an SMT mode upshift from 1 to 2 to 4 to 8, you have more logical CPUs. You can run more threads concurrently. That's what idle represents. Idle plus wait is not to traditional cores with nothing to do. It is available capacity to execute more threads on the same allocated CPU resources. That's what idle plus wait means. On Power 8 at SMT4, there's a direct mapping of idle plus wait to what's really occurring. I said idle plus wait at 2% means SMT4 mode, 3 workload threads, 1 wait process. If your idle plus wait is 0%, you're SMT4 all threads and probably over-threading. That's why 2% is a key cutoff. Greater than 40%, you've got seated and folded down virtual CPUs. You're not using all the CPUs you have, so on and so forth. The inverse of idle plus wait is the rules of expectation for user and system. They are reverse mirror images of each other directly. I'm giving you a systematic formulaic way of understanding the numbers. That's how I tune. There is no counterpart for the above on AIX Power 9. This is, what you see here is only Power 8, because the Power 9 core is so very different. Not all things are transferable to Power 9. The skipper. Those are the threads that are executing, RPW. These threads are on the run queue, are context switched that many times, right? Give me my icon. 70 threads were context switched 45,000 times in a second across as many as that many logical CPUs, 256 here. And The false CS number here, this context switch number here, is the CS number on mpstat on the next slide. This number here is the same as this number down here for mpstat. And under mpstat, this total context switch number here can be divided into ICS. This 109 is 109 of 933. This is 11 of 158. That means this 158 includes this 11 ICS, involuntary context switch threads. I told you that the ICS threads are your long-running threads. Your long-running threads, we could see under PS-EF pipe sort-NK4, those are the long-running threads where the C value is 10 or greater. When you take CS minus ICS, you get the voluntary context switch threads, the calculated. This is an implied calculation of VCS. This next set of slides regard only Power 8, but some things are true for Power 9. This is true. Threads, when they're on CPU, they either VCS or ICS. Okay. If they complete before preemption, voluntary jump off the CPU. All of our kernel processes are VCS. Okay? All of our kernel processes are extremely short, high priority execution. Or preempted before completion. That means it wants to run longer, but it got kicked off. What I'm talking about here is, why did it get kicked off? A lower priority thread running can be preempted by a high priority thread. This is a priority ICS, and this is what the kernel does to our user workload. High priority kicks off the long-running thread. Of course, priority ICS stops a long-running thread. The better alternative is the technology we exploit today. The better alternative is, don't kick off the long-running thread. Do an SMT mode upshift and run the kernel on the second logical. That's what I'm talking about here. Instead of stopping a long-running thread, which is traditional, we do an SMT mode upshift and run the kernel on the second. In this fashion, an SMT mode upshift allows the long-running thread to continue running. But there's a cost to this privilege. Every SMT mode upshift divides the core. You know, you run SMT1, go to SMT2, you divide the core by 2. You go to SMT4, you divide the core by 25. You divide it in 4 pieces, okay? Every time you do an SMT mode upshift, it shortens the thread execution durations because you're running on less of the duration of a core. It induces more thread migrations because the run queues build up. And you reduce the prefetch. The SMT mode reduces the SMT prefetch with each higher upshift. So your long-running threads get disrupted with an SMT mode upshift. That's what I'm saying. You don't just want your threads to run fast on CPU. You want your threads to run fast for as long as possible within an interval. How do you do that? You run at a lower SMT mode on Power 8, which is why I told you OLTP, I want you SMT1, SMT2. Throughput efficiency for batch workloads is don't waste any CPU, use it all up. Use SMT2, SMT4 modes. So there's a method, there's a madness that makes sense in this case. That's the whole slide. That's what you'll find in your deck. In contrast, short, fast kernel threads. In contrast to short, fast kernel threads, some threads run for a big tick. The big tick threads I'm talking about is threads running with a CP value of 10 or greater under PS-EF sort-NK4. Those are your long-running threads. I don't want my threads to be preempted early, and a long-running thread is one that runs for the full duration of a tick, 10 milliseconds. At the end of 10 milliseconds, it is involuntary context switch because it's been running too long. That's the best kind of ICS. Long-running threads are made up of long-running processes are made of long-running threads, and long-running threads running for a full 10 milliseconds is the best. So the ideal is your threads are all VCS or big tick and no ICS due to priority preemption. That's how you tell you have enough CPU. This is an ideal of what I'm trying to achieve when tuning for performance. Yeah, I'm giving you my secrets. This is how I tune. Unfortunately, if you have too many threads on the run queue or you don't have enough logical CPUs, it stays stuck in the highest SMT mode and your short threads begin preempting your long threads before a big tick. This is exactly what screws up performance. Your long-running threads get preempted and spread across too many intervals. That means your long-running threads are fragmented across more intervals, and the progress of your long-running threads is extended across, 20, 30 intervals when it could be running all together in one interval. That's what you're going to see in your deck. And I reiterate, TIDs at CP greater than 10, those are your long-running threads. They comprise your user workload, and your user workload we care to tune are these long-running threads, and it all ties back to what I'm talking about here. Premise number 3. Long-running threads is the workload we care to run as fast as possible for as long as possible in an interval, a whole new dimension. Not just running a thread fast, but running a thread fast for as long as possible. That means reducing the L2, L3 cache misses. That means keeping the cache hot and as time local as possible by not spraying it across your sharing the core with other LPARs. Long-running threads tend to anchor on the first logical. This is a big deal. Your long-running threads run on the first logical as the virtual CPU core rapidly shifts its SMT mode. When you monitor mpstat long enough, remember that. You'll see it. Number 5, short-running threads are usually or more often attended by the SMT2 mode or SMT4 modes. They're high-priority threads forcing the SMT mode upshift. This is a SUME model of my SUME model for SMT mode attention to threads, and that's what you're going to find in your deck. And I'm telling you, just from experience, the SMT mode attention to threads pivots at 5-to-1. That means for 100 total context switches, 20 of them are ICS, that reduces to 5-to-1. Here's why. When you're lower than 4-to-1, going down to 3-to-1, your big tick long-running threads are proportionally running in higher SMT modes. That's a proportion. And if you're running at higher SMT modes, your long-running threads get interrupted and are, again, spread across more intervals. There should be gestalt here in everybody, I hope. When you run at 4-to-1 going down to 3-to-1, it hampers OLT3 thread responsiveness. It means if it's sustained for OLTP at 4-to-1 going down to 3-to-1, your OLTP performance is going to hurt. Because your long-running threads that are running intensely for OLTP are running at a higher SMT mode for a shorter duration, and you're spread across more intervals, if sustained. The same quality improves batch efficiency when sustained, but it's a completely different workload. Okay, gestalt. Study this here. I'm trying to figure out what I'm saying. I gave you all the background, slides above. The other side of it is at 6-to-1. If you're sustained at 6-to-1, that's the border between enough and too many virtual CPUs. So if you're monitoring your workload and you're showing 10-to-1 all the time, well, yeah, you're sitting real pretty. You probably have too many virtual CPUs at that point. This here helps us guide when you have too many virtual CPUs. Yes, we yell at you since Power 5, don't configure too many virtual CPUs. Well, I'm sorry, but it took me all this time to tell you how to tell you have too many virtual CPUs. You got a formula for it. No more excuses, okay? So here's what I'm saying. SMT4 OLTP, run the CSICS as low as 5 to 1, 3 to 1, 4 to 1, 4 to 1, depending on SMT and the kind of burst load. There's a cool summary slide for a poster. And know that the CSICS ratio is further refined by what I'm showing you above here. You go back and forth and tune it accordingly. And this idle and weight is the inverse of U surplus system. It's very systematic. It's all simple math. One reflects the other, the inverse of the other. New topic. This here is mpstat looking at minor and major page faults. Minor page faults are JFS2 cache hits. Major is going to the SAN. Okay? Now you see these numbers all the time if you bother to look. And when you look at this here, you'll see that the major page faults is higher than the minor. That's bad. I'm telling you that your digit count, I said digit count ratio, 3 to 1, 4 to 1, 5 to 1, 5 to 5, 6 to 2, that's cool. That means there's 5 or 6 digits to 1 or 2 digits here. That's where you should be. Warning is 5 to 3, 6 to 3. If you're 3 digits major, that's a warning sign that you're getting hot. Now, I got to explain what getting hot means. If you're 5 to 4 or worse, or minor is less than major, you got a real problem. Why? That means you're accessing data that is all too new, and too little data is in memory for cache hits. What am I saying? I'm saying that if you've got a gallon of data, a quart of memory, hey, if your access data is just a gallon in a day and you've got a quarter of it in memory, you're gonna work rather well. Maybe even more memory, 2 quarts of memory would be better. But if you've got 100 gallons of data and only a little bit of memory, all you're going to do is I/O all the time. In these larger scale times with larger data and larger memories, we need to be aware the amount of data you access in a day must be properly proportional to how much RAM that you have. Okay? The ratio of access data to LPAR gigabyte RAM must be properly proportional. And from another presentation, this is a variation on my 4th principle of assumed scale of design. Uh-oh, someone's running out of time. The skipper, CSICS, ILCS, VLCS. The heck? CSICS is threads migrating among logical CPUs inside the realm reality of AIX. ILCS, VLCS is the war of virtual CPUs for the core with the virtual CPUs of other LPARs fighting for that core. CSICS, threads within AIX. ILCS, VLCS, virtual CPUs fighting for the core with other virtual CPUs of other LPARs. This is between LPARs. This is inside of an LPAR. CSICS, same thing, different syntax. But I want to use this. This is easier. See, ILCS, involuntary logical context switch, is events stealing the core to run hypervisor, which usually happens below entitlement, and it's also meaning stealing the core when running an active workload. That means you're running beyond EC. Very few of us have been monitoring ILCS, VLCS because these 2 columns are not in the world's favorite AIX tool. If you don't see the numbers, that whole reality doesn't exist, which is why I bring this up. When you are running beyond entitlement, everything looks the same until you see this output. When you run beyond entitlement, that means the PC value down here is 56. You have 46 entitlement. What happens is at that point, ILCS sharply goes up. What am I saying? I'm saying that these numbers are a virtual CPU on a core with an active workload, and we yank the core away. You steal the core from an active workload. That's what happens when you run beyond entitlement. That's bad. VLCS is releasing the core because the core virtual CPU has nothing to do. Or it needs to seed or convert or fold or migrate, right? I mean, the thing is, it's got nothing to do, and this happens below entitlement as well as beyond entitlement. This is excess CPU or too many virtual CPUs, and going back up here, this is not enough entitlement. What am I saying? I'm saying entitlement controls this value. I'm saying the count of virtual CPUs controls this value. You can't sensibly monitor these two values as a ratio. You got to see them as two loosely related factors, and we go right to this. If this ILCS, it should be, should be below 3 digits, or 3 digits at the most, instantaneously. If that's too high, you add entitlement. That's what this means. To reduce that, to increase entitlement, to reduce ILCS, and the inverse. Pretty simple. VLCS, completely different. Remember, VLCS is excess CPU with nothing to do. Well, how do you know what's high and what's low? Well, I'll tell you right now. If you ever see 20,000 sustained every second, you have too many virtual CPUs with nothing to do. And I give you this year to guide. Depending on the amount of memory, you should have some range of that, and you adjust it by tuning the count of virtual CPUs down, because nobody has too few. Everyone's got too many. Going to iostat. This is iostat, 1 60-second interval, and we're going to go through those 4 colored columns. That may be hard to see, so I'm going to zoom in on the left, zoom, and look at percent time active in a 60-second interval. What's high or what's low? I'll tell you. 60-second interval, assuming OEM's enterprise class SAN, not your internal SAS drives, okay? So percent time active is the active percent over an interval of 60 seconds, saying that that's 69.2% busy in a 60-second interval. That's rockingly busy in 60 seconds. Mind you, these numbers are all about 60 seconds, not total uptime. If you're less than 30% busy in a 60-second interval, perfect. 30 to 50, sweating when sustained. Usually it's not sustained. 51, all the way up. Hey, critical ICU. When I say call OEM 911, I mean you're calling this SAN storage administrator 911 service, support. Don't really call 911. And you see that these are more than 90% busy in 60 seconds, some of them. And that's a real problem. Okay? For confidence, don't just go by this rule of expectation alone. Use it with all the others. Let's go to next. Hey, this is average read service, right? So I talk about what you should expect on today's OEM SAN storage. None of you are running on SCSI 3 direct attached disk arrays anymore. But that was where the first standards were started. Back in those days, if you were less than 10 milliseconds on reads, cool. No more. It's 1 to 5 milliseconds today. If you're averaging greater than 20 milliseconds for reads, you got some critical issues. Read max service. See that capital S? It means seconds. See this capital S? That means the maximum reads took more than a full second in the last 60-second interval. I kid you guys not. Twice since 2002, it was not a capital S here. It was a capital M. Yeah, that's minutes. Now I'm looking for my first capital H. I haven't found it yet, but I'll keep looking. So that's long running. This is a real problem, okay? So understand what's long running, because when they occur probably across the whole concurrent shared RAID set, and all goes bonkers, everything goes crazy. So look for that. Here's the run queue, queued up full. Numbers, 1, 2, 3 digits. Here's those 3 digits sustained. This is the worst case possible. And when you've got all of these things going so badly overwhelming, when all the SAN storage is running this badly on Ginger, it comes down and looks like this on the W column. I told you to begin that Ginger had problems with SAN storage. At 3 digits critical, well, it's because it looks like this, with this, given that, and a blown away Q depth. So it's a direct monitoring that when you watch this, you can know, you can see, you got storage problems. This is valid for Power 8 and 9. It's true today. Okay? So I showed you Ginger going through my favorite tool. And it's the same thing with ARIA for Power 9. It's where it begins. This is where it ends. Then do this. Gilligan didn't die from that. And when I say do this, for Power 8 only, I'm giving you a 5-tier standard for how to build an LPAR. It's not just a simple standard. Down here, Tier 3 is the Seagull. That's the scavenger LPAR. That's your red-haired stepchildren. And as tier -1, that's your high-performance priority LPAR, and you build accordingly. What is the column width of? Almost done here. Next time, Joe. Here's my rules of expectation. I'm still learning Power 9. I'm going to tell you more next year. Most of this is Power 8. And depending on the capability of your infrastructure on the floor, all this could change, but not much. Ha-ha! That's who I fell in love with when I was 8 years old. Joe, to you.
Okay, Earl. Well, you finished before the time was up. I'm impressed. Really didn't think that would happen.
200 slides.
Yeah. So, we have a bunch of questions. Well, I don't want to say a bunch. We have some questions in here, Earl. But really, let's go back to one anyway. You made it kind of an broad statement of never run SMT8 on Power 8. And more than a couple of people were like, oh, hey, so why is that and what's the rule? And I think there's probably some exceptions to that rule as everything. But why don't you explain a little bit about that?
The main one is that when you're remember, you can be setting hard SMT8, but never run an SMT8. So, if you never run in SMT8 mode, but you set hard for SMT8, you waste hypervisor overhead hunting for opportunities to shift to SMT8. That's one. 2, SMT8 mode on Power 8 turns off. It literally shuts down instruction prefetch. Okay? So if you're running in genuine SMT8 mode, your instructions are not prefetched into the L1 instruction cache, and when you miss on instructions in the L1 instruction cache, it's a hard access of DIMMs every freaking time. Right? Next, when you're running in SMT8 mode, the kernel is always running. Remember, the kernel is always running, and is running at higher priority. So what happens is that you'll shift into SMT8 mode to run 1 or 2% SY kernel, and you'll be remaining SMT8 threads will remain at 98% idle. And if you don't believe me, go ahead, run mpstat on an SMT8 LPAR, and it'll show you exactly what I'm saying. You're wasting a hell lot of CPU running a minor amount of kernel in SMT8 mode, and the rest of that interval, that SMT8 set of threads are idle. Dang, if people don't believe me, I have to prove it to them, and then they, have a hard time with it.
Well, I think it's good information to know, and it's good information to know in Power 9 that the chip technology has changed, and SMT8 runs very well. We've got, more engines and registers in there to take care of that stuff, right?
It's completely different.
Right. So with that, we're really out of time. So I want to say thanks to you, Earl, for again jumping up and giving us this great. I think it's all real useful stuff. Things that people can study and apply immediately. It certainly gives everybody lots of chance to dig into this a little bit deeper with all your slides and study it a little bit more and apply it to their exact situation. So thank you, and we'll look for more performance tuning stuff for you from you for next year, definitely.
Every year a new curriculum, everybody. I'm not going to stop developing this.
Keeps you busy.
Thank you, Joe. Thank you, everybody.
Okay, and happy Thanksgiving to everybody that's in the U.S. Great, have a great holiday, and everybody else around the world. Many thanks for all of you to be part of the Power Systems Virtual User Group as well. So with that, so long.